Good afternoon and welcome to our next part of our webinar series about precision farming and space data. Thank you for answering our initial poll. I will end it now and share the results with you. Our question was, what space-based support tools for soil are most interesting for you? And the winner for today is the soil organic carbon monitoring, which is one part of our presentation, and it's something that we've also addressed during our last year's webinar series on regenerative agriculture that can be found on our YouTube channel. So if you will like to know more, you can always go back to our YouTube channel. But let's move to the presentation. I would like to welcome you at the episode 3 of our DynaCrop webinar series, which is focused on soil use cases. This is a webinar series where we're discussing the use of space data in precision agriculture. It's already the third part. If you missed the first two, they are available on our YouTube. You will also have the link in your email after this session. And in 1 week, we will have the last final piece, which will be regarding the orchard and vineyard monitoring. But first of all, let me introduce our company. Our company is called World from Space. It's a 5-year-old company from Brno, Czech Republic, focusing on using the space data for agriculture and food production value chain. We've got a track record working with the European Space Agency, or EUSPA, and also ongoing research with agriculture universities and big farmers. This webinar is organized with the help of the EuroGEO eShape project under the Horizon 2020 program. So we would like to thank for this opportunity to have a collaboration with other companies and research institutes in the field of Earth observation. But let's move directly to our today's topic. We will discuss soil and how satellite monitoring can help soil monitoring and soil sampling, and also the water detection over the crop fields, and how this actually can be covered by our product called DynaCrop. But let's look at the current situation. It's not that funny as it might look like. We've got a big problem with the soil, and that's also why the EU has the soil as one of their key priorities at this year's, because it's very easy to lose the soil, but it's very hard to produce it back. So as you can see, it takes about 1,000 years to produce 2 to 3 centimeters of soil with the natural processes. But today we can see that already 1/3 of the soil is degraded, which means it has been overused, it's facing soil erosion, or it's toxicated. And by 2050, if nothing changes, this could rise to almost 90%. So this is a big threat to the future, which is also threatening livelihood of 3.2 billion people. So quite a lot. And we need to take into account that soil erosion can be up to 1/2 loss in crop yields. So there might be serious food shortages in the future caused by the soil depletion and soil degradation. So that's why we're looking at the soil today. And let's look how the satellite data can help. So what are the key advantages of space in soil monitoring? So the first one is the large scale. We can really look on soil in large scale, which means not just one field or multiple fields, but the whole countries or whole region, or even all the fields that we have on a planet. That's why, because the satellite data infrastructure is global, so it's monitoring all the land that we have on Earth, which is suitable for agriculture, and it gives the data about all of it. It provides the information which is valuable for different kind of agricultural practices, and it's affordable. That's the key requirement on the data, that the data is not very expensive, it wouldn't bring the benefit which would be enough for making it useful. So that's why we are using satellite data in providing the analytics about the soil. And the main use cases that we see today on the market already and in use are this. It's soil moisture monitoring, looking at the water available in the soil. Then soil salinity monitoring, which means if some soil is becoming, if there is the content of salt in the soil. Soil erosion, which is one of the problems that is the soil facing. Then soil organic carbon mapping, it's the winner from our poll at the beginning of the webinar, but also it's the most important topic which is being discussed now, also in the scientific and the business community, how to connect the climate change mitigation, climate change adaptation, farming together, and it leads to monitoring of the content of carbon in the soil, which is critical both for the yields, but also for getting the carbon out from the atmosphere into the soil. And as I said, it's something we've already discussed last year, so I would like to welcome you to see the episodes from the last year as well. Another use case where the space data is used today is soil sampling, taking the samples of soil to analyze nutrients and to optimize this process so it brings more information at lower costs. And the last one is the soil pH mapping to understand these characteristics of the soil. And let's look directly into some of the use cases. Again, we have for you one demonstration field where we will show all the information. And this field is again located in the Czech Republic. It's got around 25 hectares, so it's a quite larger field in the European context. The typical crop rotation on it would be spring barley, maize, and white mustard. The soil is fluvial, so it's not dark soil as discussed last time, but different type of soil with the elevation around 100 to 200 meters above the sea in the temperate oceanic climate. And what is especially interesting here is that here in the northern part, you can see a lake. So standing water, which has a direct effect on the availability of water in the field, but also on the waterlogging and other characteristics that we are monitoring. So it's very interesting place where a lot of the theory can be put into practice. And we will start with the focus on the soil sampling, because it's one of the key activities that are done in agriculture today to understand the soil quality and the content of the nutrients, the physical properties of the soil. And it really enables the targeted applications that we are seeking in precision farming, because the precision farming has the idea that each part of the field needs a different treatment. And to really set up this treatment, we need to understand what is in the soil available for the crop. And to do this, the companies and the farms are doing soil sampling, which means you take a piece of the soil, send it to the laboratory, and then you have the whole understanding of what kind of nutrients or elements are there. And this is critical for the baseline law of the minimum, which states in agriculture that it's not important how much of the elements or nutrients are there, that the critical one is the one who is at the lowest. So if there is not enough phosphorus in the soil, you can add a lot of nitrogen, but it will not lead to a success in your agriculture strategy. So to understand how to do the soil sampling and how to optimize it, space data can actually help you to lower the cost and increase the quality of the soil sampling data and the product that you build after it. And let's look at how we do it. So the first approach is similar to the approach that we've discussed already last time during the fertilizing use case. which means understanding the yield potential of the field and then adjusting the soil sampling to the yield potential zones that we have in the field. So the steps, again, are similar. We need to assess the field heterogeneity to understand if really the field is suitable for precision farming, to see the zone stability, and then calculate the long-term zonation or yield potential. And based on it, create the sampling maps. So we can look at directly the individual steps. So we use the lie yield potential in this example for each crop which was on a field. And we can see that the field has quite high heterogeneity, but we can also see that the zone stability is not that it's not that stable as we, for example, saw in the last webinar. It differs in the years. However, in the last 3 years, it looks more or less stable. So this is why we can use the yield potential as one of the input into the soil sampling maps. So we have this baseline map of the yield potential. And the alternative to this, if we see that, for example, the zones are not stable, or we feel that the vegetation response is not the right tool how to look at the field and the soil, we can use directly the soil organic carbon monitoring. This is based on understanding mostly the top level of the soil. So as with other satellite data products, we are always talking about the top layer of the soil, not about some deep layers. So understanding the top level of the soil and basically its brightness. So to estimate soil organic carbon, we use this kind of soil brightness assessment, which is based on 2 different indices we've got in our system. One is basic, and one is performing better in places where you have quite high content of some elements connected to iron or other metals. So here we look at these characteristics. First of all, look at the terrain, because similarly to what we discussed last time, terrain is really important input into understanding the field and also the soil. Because, for example, on this field, we can see that on the southwest part, it's part which is quite elevated, and then it's going down, and we have some drop in the middle of the field, which usually happens that some of the nutrients or the elements are basically going down with the water. So there is usually also higher carbon content, so organic carbon content in this lower part, which is somehow also can be seen on this map. So this is the basic analysis of the soil organic carbon in the field. And this is again division of the field into the zones with the different soil organic carbon content. The limitation of the satellite data is that it doesn't give you the absolute amount of the soil organic carbon, so it's not tons per hectare, but it's relative. So it says where it's more and where it's less. And then it's used together with the soil sampling to actually get the right values that have the information about the whole field, which is relevant. And if we have this kind of a map, we can then create the map for soil sampling, so the places where the samples should be taken to have really the qualified information about the whole field. And then there are different strategies that the soil sampling companies are doing. It can be creating these points around center line, or it can be per hectare, or it can be in the zigzag patterns. So it's also catching up some intra-zone variability. And the other parts, if we are creating the map for soil sampling that needs to be taken into account, are again the topography. that's clear, but also the soil type, because it's very different based on the soil type that is on a field, and the crop rotation, because for each crop before and after it's a bit different, where the output was how much nutrients were taken by the plants in the different zones, and also then if we create the prescription for the applications, it's also very important information. So this all needs to be put together, also answering some other questions that usually the farmer knows already. Like if there is some extraordinary place that needs to be taken care of, or there was some thing happening in the last year which we didn't capture from the satellite data. And what are the advantages? Why to actually optimize soil sampling with the space data? So the important thing is that you can use less samples for the same area, so you save the costs for the laboratory, but also you get the more relevant information. Here we have some comparison between the regular method, which is being done without the satellite data. It means having a pattern that is followed. For example, each 250 meters, you take the sample. And then if you create the map, you can see that it's got a different granularity and also the different information in several zones. Then if you really if you take the samples in a way that it respects the production zones in the field. So that's the lower picture. Based on this, the farmers are able then to reduce the consumption of the fertilizers by additional 5 to 10%. Not only fertilizers, it's also other nutrients or elements that needs to be put on into the soil. It's also increasing the long-term soil health because it's get the better information, and in total, if we count that we optimize the soil sampling, and then we also optimize the applications based on this, the farmer can expect 10 to 20% increase in yield, which is already a significant amount, which really pays back this whole process. So that was the first use case. And we will move to the second one, which is about soil moisture. Understanding the soil moisture is very important in agriculture, especially in specific stages. For example, for the seed germination, it's important if there is no water, the seed is not growing. That's clear. But also in other parts of the phenological stages, there are different needs of the plant for water. So understanding the soil moisture is critical at several parts. Also for nutrient uptake, the soil moisture is critical. The plants are not able to uptake the nutrients from the ground if there is not enough water, which can make some of the applications useless. For example, fertilizing, the mineral fertilizing with the solid parts during the drought periods doesn't work. And it's important to plan the operations on the field also based on understanding the soil moisture. So to address this need, we're working with the soil moisture maps, and we create long-term soil moisture maps, and also the time series, so the farmer can understand if there is above average or lower average soil moisture at the moment, and what's the trend, which can be critical. And also comparing it to the long-term averages and the same situations in the previous years is quite valuable information for the management of the farm. So let's look at how we do it. So to assess the long-term soil moisture, we're always trying to find this underlying pattern. So where is usually more water and where is usually less water, which also means in which parts the crops are more affected by droughts and in which part the crop is more drought resistant or more resilient. At this field that we have here as an example, we can again see the impact of the terrain. So the parts that are upper and higher, we can see that they don't have that much water as the parts that are generally lower. And we can also see here that there is some kind of impact of the water body, which is above the field. But these parts that are closer have also more than average water available on the field. So we create this long-term map, which gives the basic understanding of the division. And then we're using Sentinel-1 data, so data from radar satellites that are independent on weather. So it means that every 2 days, you have the information about the soil moisture on all of your fields. The index is it's working very well under some vegetation cover. So it doesn't work properly when you have 2 meters of corn on a field, but at the first half of the season, it works very well. But then also for the farming, it's more important to understand the canopy water content, so how much water is in the plant than in the soil. So it's not that huge problem. And we have again example here from our field and the comparison between precipitation, so the amount of the rain, and our SME index, and we have 1 day here highlighted. So it was last year, and we can see that in March and April, there was hardly any rain. You can see that the soil moisture index is going down. And at 30th of April, this was the situation on the field. So the soil moisture was very low almost everywhere, but there were 2 places where there was still enough, which can be connected to the terrain. That's the first thing. And the second thing, it can be connected also to the water body, which is nearby, and there can be some high groundwater levels that still support the field, so it has some kind of soil moisture available. And then in May and June and July, we can see that there was rain, so the index is going up. It's about normal during the summer, and then in autumn, when there is not enough evapotranspiration and the water is not being consumed by the plants anymore, the index goes up again. So this is the soil moisture index that we are using to capture the trend and the current situation, which is really good for planning of the operations, like this seeding or applying the production fertilizing during the season. And we're also working on measuring this on the ground to verifying of our information with the ground truth and the ground sensors. Here you can see some of our experiments. On the left, it's very easy when it's dry soil, but in the middle, we have found out that you can also measure the soil moisture content by the amount of time you need to get the car from a field. And if the field is wet enough, you need to use tractor. So this is something we've experienced, I think 2 weeks ago, that there was just so much soil moisture that we couldn't get out with the field, and then we have to clean the car as well. So we're not using only satellites to measure the soil moisture. And if we sum it up, what are the advantages of the soil moisture monitoring? So the first one we discussed is the saving of the fertilizer. Mostly it's in combining the soil moisture and the yield potential into the application map, but also it's while saving the by making better decisions at when to actually fertilize, if there is enough soil moisture or not, so the plant can actually uptake the fertilizer. Again, there is the similar results for seeding. So this can be 5 to 10%. Again, it's by combining the yield potential and soil moisture maps, or by the right timing of the seeding. So seeding at the time when it makes sense. Also, it works pretty well for drought mitigation, for understanding which parts of the farm, for example, are mostly suitable for irrigation, and if there is just a limited amount of water available, which fields are the most vulnerable to droughts, so where the irrigation could actually make the highest sense. Then with the water savings, that's something we're not working on at the moment, but there are other Earth observation companies that are working on the prescription maps for irrigation. There can be 15 to 20% better use of water while irrigating the fields. And this, of course, overall, the target is still the same, increased farm efficiency, and when possible and sustainable, also increased crop yields. So that was our second use case. And we will look at the last one, which is a shorter one about the standing water, which usually is at the fields where there is a problem of waterlogging. So there is a water which is regularly going to the field and affecting the yield and the quality of the crops. So how do we do it? We have two products in DynaCrop that we are using for this. The first one is normalized difference water index, which is very good for standing water detection, but it doesn't work under the vegetation. And the second one is called water in wetlands, where this is very useful for identification of waterlogged soils, and also it's working under the vegetation cover, so it's much more useful during the season. And here we have the example from the field, from one of the waterlogging situations. So here is the field, and this is the true color image from a satellite. So you would say that there is actually no water. If you use the NDWI, the normalized difference water index, you can see that here is the water body. So the water is well defined, and you can see small part of the field. But with the water in wetlands index, you are actually see the whole area which is covered by water, or where the field is waterlogged. So it means there is really high content of water in the soil. And this can be then used also for statistics. So, for example, on our field, the green parts are the parts where the waterlogging is happening, and the more green the color is, means that more often waterlogging is happening there. So this is the area where it's happening the most. And we could also see that it's the part where there was the only place where the soil moisture was available, also in the drought period. So there is definitely something on the field happening in this place, maybe with the groundwater, maybe with the dip. And if you're looking at some specific examples, standing water detection is very important for rice monitoring, because the rice fields, they need to have some amount of water during the season. Also, you can, when it's in places like Greece, you can detect some kind of phenology from it, because you know at which growth stages the field needs the water and when the water is being put there. So this is an example using the data at rice fields in Greece. So those were the examples from the soil moisture. This is a part of our work that we like, of creating the prescription maps for fertilizing, seeding, or soil sampling. So the idea that we like is to create the maps that understand the heterogeneity of the crop and the soil, and to improve the management of the field based on this. So this is something we have already done and automated in our system called DynaCrop, and we invite you to check it if it makes sense to use it for you to assess this kind of information, put it into your product, and then get it directly to your customer or end user. The system is white label, so you don't need to mention that it's coming from DynaCrop. You can put it into something that you do. It works globally. It's very easy to integrate. The first integration can be done in 1 day. Then the more advanced in upcoming 2 weeks, 2 to 3 weeks, and then you can already use it in production. And we are here to help you with the specific use cases and the sales support, because we understand how this is being used and sold all over Europe and also in 3 other continents. So this is the end of the webinar, and we will have time for questions and answers. Before you fill it, I would also like to invite you for our last episode, which will happen on April 27. And we will talk mostly about orchards and vineyards, but we will also mention some other edge cases that we are on which we have worked with our partners and customers. So let's look at the questions. So the first question: how usable is soil organic carbon index in no-till fields? That's a very good question. It's not really usable, because if you have a high amount of crop residues, or if you have all the time some kind of cover crop on the field, the soil organic carbon indexes are not working well. So for this, it's better to use another approach to soil sampling. For example, with the use of the yield potential, not based on the soil organic carbon assessment. Another question is: do you calculate SME purely from Sentinel-1 data, independent of graph-through measurements? And can you elaborate more on how this is calculated? Also, are there any of your data products, such as Leica, available for other applications? So let's take it from part to part. The SME is calculated purely from Sentinel-1, so it doesn't need any ground-through measurements. However, if you have a ground-through measurement, it can be used to calibrate the data, and we're working on a methodology how to translate it into the volumetric measures. So into understanding the soil moisture, not in relative, but in absolute numbers. How this is calculated, I will not disclose here, but it's based on the methodology which has been developed by scientific teams, and it's not something which would be completely unique for us. It's a methodology which in place also in other places in Europe. And the last part of the question: are any of your data products available for other applications? Yes, so that's the key business of us, that these parts are available for you, so you can put it into your products and then sell it to the end users or your customers. And for Leica, the weather-free leaf area monitoring, we will be starting the testing with the users in about 2 weeks. So if you are interested, we will give you the early access to Leica as well, so you can test it with your fields and your data. We'll be very happy for any feedback. So come back to me or to any of my colleagues, and we can discuss how to do this. So what are the differentiations regarding the costs to other companies that are doing the similar things? That's a very good question. Our costs are €1 per hectare and year. That's the base price that you pay for using the DynaCrop. If you do it on an automatic way through the API, if you need any help with it and some analytics or other works above, then we always discuss on an individual cases. Usually we start with some pilot projects that then can grow into the larger monitoring. So €1 per hectare is the usual cost. For example, if you do soil sampling, usually it would cost you about 20 to 25 euros per hectare. So with €1 extra, it's not getting the price somewhere else, still available for the customers, but it's giving them much higher value, and also can save the soil sampling time, because usually the soil sample needs to come 2 times to the place, first to understand the field and then to do the samples. But then the first part can be done with the satellite data. The link to YouTube will be shared. You will get it by email to which you registered, so don't worry. And then we have technical questions on what types of errors do NDWI and WIWI make. This I will ask my colleague Matusz to answer you in this Q&A. So if you wait for a moment, you will see the answer under your question. Then what does SME value 1 mean? So the SME has got values between 0 and 1, and 0.5 means that this is the average soil moisture on a field. Then SME 1 means it's the total capacity of it's the highest soil moisture that we can measure. So it's the edge case in the field. But also maybe when you are ready, Matusz, with the first question, you can give some answer also to this question. Can you please specify the fertilizer application? I missed that part. This was part of our previous webinar on the field crops. So you will get the link about the video where you can find this video in email, so you can then check it and come back to it. And if you have any questions, don't hesitate to come back to me or to my other colleagues. So this is the contact. If you would like to contact me directly, you can use LinkedIn, mail, or phone, or directly book a meeting with this QR code. And we have also the end poll. And to the question, what do you consider major challenges regarding soil health? We can see that the highest share is by the soil biodiversity lost, is for 50%. There are no other questions coming, so I would consider this done. Thank you for your attention. We will be happy to meet you again in the next week during our last episodes on orchards and vineyards. And meanwhile, if you would like to talk to us, we are happy to discuss your specific use cases or problems or questions. Thank you for your time today, and have a nice week.